The next instruction is called add. The add instruction allows to add numbers. It looks like this: add destination source. Maybe at this stage you are not very surprised, and you are going to see that for many instructions in the x86 family, it goes like this: destination and then source. These are the usual arguments for instructions with two arguments. The action that is going to be taken is something like this. Destination is assigned the value of destination plus source. Destination is going to be changed, and source is not going to be changed. It will stay the same. Another important thing, you might be wondering what happens if the result of the addition is too large. Maybe it is bigger than 32 bits. The result wraps around if it is larger than the size of the arguments. The wrapping around depends on the size of the arguments. If we add two numbers of size 8 bits, then the result will wrap around in size of 8 bits. If we add two arguments of size 16 bits, the result will be modulo 16 bits. The same for 32 bits. Some examples. Add EAX, EDX. This adds the contents of EAX and EDX and stores the result in EAX. Something like this. If you are more into mathematics, you can imagine that here, instead of EAX plus EDX, we have EAX plus EDX modulo 2 to the 32. Because this addition is modulo the size. Another example. Add ESI 11B. This adds the number 11B. You might be wondering, what is this B in the end of 11? This B means binary. This number should be read as 1, 1 or 11 in binary, which is 3 in base 10. This instruction is going to add the number 3 to ESI. Eventually, we're going to get something like this. ESI is assigned the value of ESI plus 3. Another example. Add DX SI. This adds the contents of SI to DX and stores the result in DX. Note that this is a 16-bit addition. Contrary to the previous ones, this one is a 32-bit addition, and the next one was also 32-bit addition. This is a 16-bit addition. So the wraparound is going to be in 16 bits. As usual, we're going to have some invalid examples, just so that you know to avoid it. The first example would be add 532 in base 16 ECX. What's the problem here? 532H is a numeric literal. It cannot be the destination of the addition operation. We always have to make sure that the destination argument here is some kind of cell or place that we can store data. A number or a literal or a constant is not a place to store data. This number is just a number. We can't store the result in there. We always have to ask ourselves, where will the result be stored? Another invalid example. Add BX EAX. Here the problem is with the sizes. BX is of size 16 bits. However, EAX is of size 32 bits. And the sizes don't match. There is no such instruction as add BX EAX. Therefore, the assembler won't be able to encode it in its equivalent numeric representation, because there is no equivalent numeric representation for this kind of instruction. It is invalid. The same goes for the previous one, which is invalid too. Some example for the add instruction. Take a look for a moment at the instructions just to try to guess what is going to happen. Here again, we assume the values of ESI, EAX, and EBX. These are the initial values. This time we don't use the question mark just to be more efficient so you can see faster the results. If there were question marks here, the result of add EAX, EBX will be mostly unknown. It will be also a question mark. So we are going to try to add EAX and EBX. Actually, that means 2 plus 3, which is going to be 5, and it is stored inside EAX. Another instruction, add EAX, EAX. We are going to add EAX to itself, and then store the result in EAX. Can you guess the result? I hope you guessed it right, and indeed it is A, because A means 10 in base 16, which is 5 plus 5. If you guessed 10 instead of A, maybe you should go back and review the lessons about base 16 to make sure that you understand those things well enough. Another instruction, this time this is move. We are mostly talking about add here, but I think some interesting move in this sequence of instructions can actually make things even more interesting. So indeed, we have this F thingy put inside ESI. Now we are going to add EBX and ESI. This is maybe the first interesting or very interesting thing in this table. And why is that? Because ESI is already a very large number. If you think about it in binary terms, it is made only of ones. And we are going to add this number 3. We are expecting to see some kind of wraparound. What result are we going to get? Try to think about it for a moment. Actually, we are going to add 3 to the highest possible unsigned number. If we just add 1, we are going to get 0. And then we are left 2 units to add. The result that we expect is going to be 2. That is because 3 plus this number is going to be 2 when wraparound is considered. Another interesting instruction, add ESI, EAX. We are going to add those two numbers, the F's and A, and put the result inside ESI. Again, we are going to get a similar effect. There is some interesting effect for adding with this number, which is equivalent to decreasing by 1. We expect to get something like 9, which we get. Another example of add. This time we are going to try to add partial registers. We picked some registers with initial values, and we are going to try to add some strange parts of them, just so we make sure that we understand how things work. Mostly the part of the wraparound, which could be confusing sometimes, but it is not going to confuse you because you are tough. The first instruction, add AL-CH. AL is the lowest part, which is FF. And CH is this 7. So what do you think is going to happen here? We're actually going to add 7 and FF, which is going to result in a wraparound. But this time we are adding bytes. We are adding sizes of 8 bits, which means the wraparound is going to be constrained to 8 bits. It is not going to be above the 8 bits or outside of it. It will be bounded in this place or in this place. So let's see what happens. We got 6. And why is that? We added 7 and FF, and in the real world we should have got 106, something like that. Let's check out our calculator. If we are going to add FF plus 7, okay, and try to see the result is 106. So where has this one gone to? It was trimmed. You can imagine that it is non-existent, and we only took the lowest 8 bits, the 6, and put it inside AL. Next one, add DI-CX. DI is the lowest part. Actually, DI equals FFFF. And we are going to add CX, is the part here, the lowest 4 nibbles. So we are going to add these two parts, and again, the addition will be only constrained to 4 nibbles, or to 16 bits. That means that the wraparound is going to be inside those 4 nibbles, or inside the 16 bits. And we got 702. Again, those F's have this strange effect of decreasing by 1. Another instruction, this is a simple move instruction. It is just going to override EDI. And we got the same EDI like the last time. And another instruction, add EDI ECX. This time it is going to be a bit different. If you remember last time, you can even see it here, we added CX with DI. This time we are going to do addition of 32 bits, contrary to the last time that we did addition of 16 bits. Then we are expecting a bit of a different result. We are going to add this number, 703 in base 16, to this full number, which is a pretty large number. Mostly we expect to have 702 here too, as the result. However, this time it is not going to be wrapped around only in the boundary of 16 bits. The addition is going to affect also the next digits. You can see it here. Try to look at it for a few moments. I also recommend you, maybe if you didn't follow everything, the last digit, maybe to view this part again, because it is very important that you make sure that you understood every instruction that you saw here. Let's move on. Important point, the wraparound is done according to the size of the argument. This is something that you should take with you from here. We've seen that there were some kind of additions here. This addition was in 8 bits. This addition was 16-bit addition, and the last one was 32-bits addition. Each of them had some kind of different effect, because the wraparound was bounded to the size of the arguments. The sub-instruction. The sub-instruction subtracts numbers. It looks like this, sub-destination source, which, as I mentioned before, is mostly the usual. The operation is like this. We calculate destination minus source and store it inside destination. Just like the add instruction, the result wraps around if needed. What does it actually mean? It might be a bit difficult for you to imagine what does it mean to wrap around for subtraction. And I can give you a hint. If you think about the subtraction as addition, just like we did in the 2's complement examples, then we get something like this. That the subtraction is equivalent to addition with the negation of the source number. So instead of destination minus source, we get destination plus the negative of the source. And the negation is done using the 2's complement method. Examples. Sub EAX EDX. This subtracts the value EDX from EAX and finally stores the result inside EAX. In another form, EAX minus EDX is stored inside EAX. Another example. Sub CL DL. This example subtracts DL from CL and stores the result inside CL. In another formulation, CL minus DL is stored inside CL. Another example, sub ESI 4H, which means 4 hexadecimal. This instruction subtracts 4 from ESI, from the ESI register, and stores the result back inside ESI register. In a bit of a simpler formulation, ESI minus 4 is stored inside ESI. As usual, we are going to have some invalid examples, which are not very different from the previous invalid examples that we had. For example, sub EAX DL. The problem here is with the sizes. EAX is of size 32 bits, however, DL is of size 8 bits, and the sizes mismatch. There is no such instruction. You cannot encode such instruction to the x86 processor. Another invalid example, sub 1AH DL. This is just a constant or a literal, and we cannot store the result of this calculation inside a literal. This literal is not some kind of cell or location or place in memory. No, it's just a constant number. This kind of instruction does not exist. You cannot encode an instruction that will have the equivalence of this operation. Values for the registers EAX, EBX, and ECX. We put inside some simple numbers, 2, 3, and 1A, and we are going to look on the effects of some of the instructions. The first one is sub EAX, EBX, which is going to subtract. It is going to execute EAX minus EBX and store the result inside EAX. So EAX is this number, 1A, minus 3. Can you calculate it in your head? 1A minus 3 should be 17 in base 16. The next instruction is addition. I put it here just to make the example more interesting. I know it is an example about sub. Add EAX, EBX. The last instruction was about subtracting EBX from EAX, and now we are adding it again, so we expect to get the original value of EAX. Maybe if we literally look at it, we are going to add 3 to 17, which is going to be 1A in base 16. And we get this 1A. Maybe if we look at it a bit more generally, these two instructions complement each other. They do the opposite. This one subtracts and this one adds. The next instruction, sub ECX, EBX. We are going to subtract 3 from 2. Can you guess what are we going to get here? Let's see the result. As mostly expected, we are going to get those F's because 0 minus 1 is going to give us this interesting number. The next instruction, add ECX, EAX. We take this number, which is made of all F's, and add EAX, which is 1A. Can you guess the result? I can remind you that adding to the F's has the strange effect of be equivalent to decreasing the number. Indeed, we are actually going to get 9 as the result. The last instruction, subtract CL, AL, is going to subtract the value AL from CL and store the result inside CL. Let's look at these values. AL is 1A and CL is 19. So we are going to do 19 minus 1A, which is going to be negative. Try to guess the result. You guessed it right. It equals FF. It is very important to note here that the wraparound was only of size 8 bits. For example, we didn't get F's all over the place, only for the lowest 8 bits, because the two arguments were of size 8 bits. Remember, wraparound is done according to the argument size. This is both true for the add instruction and also, as we see here, for the sub instruction. Summary. Move copies data from place to place. Maybe copies is the right word here because it doesn't move the data. The data doesn't disappear from the source. It is just copied to the destination. The add instruction adds numbers and the sub instruction subtracts numbers. Some exercises. Finally, we can do some more exercises after talking about history and the theory of things. You are going to do some code reading and predicting the resulting values of registers. That means you are going to look at some code and try to predict what is going to happen. You are going to do some code writing. That means that you are going to write some code to do some very simple things. And it is going to be very simple mostly because you only know at this stage about 3 instructions. Make sure to solve everything before moving on. I talk about everything. When I say everything, I mean everything maybe besides the bonus exercises, which are not mandatory. This is very important for your understanding of the instructions and of the registers. It is very important to remember this. You could just float away in this course and maybe see all the lectures. It won't make you very smart. If you want to understand new things and know how to program, then you have to do the exercises. They are going to make you tougher. See you next time.